the evidence. How often AI gets security wrong. Before we dive into specific vulnerability patterns, let's look at how widespread the problem actually is. This section walks through independent research, real studies with real numbers, so you can see exactly how much extra scrutiny AI-generated code deserves. The short answer? Far more scrutiny than most developers apply today. 7 independent research efforts from university labs, security companies, and production telemetry have examined the security quality of AI-generated code. They used different methods and tested different AI models, yet they all reached the same conclusion. AI-generated code carries significant security risk. Let's walk through the first 4. Stanford published at ACM CCS 2023. 47 developers were given 5 coding tasks in a controlled experiment. The result? Developers using AI wrote significantly less secure code on 4 out of 5 tasks and were more confident it was secure than developers who worked without AI. NYU published at IEEE 2022. Researchers generated 1,689 programs using Copilot across 89 scenarios. About 40% of those programs contained at least one exploitable security vulnerability. Veracode 2025, across 80 tasks, over 100 large language models, and 4 programming languages, 45% of AI-generated code failed security review. Java was the worst at 72%. Cross-site scripting tasks failed 86% of the time. Armis Trusted Vibing Benchmark 2026. 18 AI coding models were tested against 31 scenarios, and every single model failed at least one security-critical scenario. That is a 100% failure rate. The weakest areas were memory management, authentication, and file handling. Different groups, different models, different time periods, yet the same conclusion. AI-generated code carries significant security risk. Now let's look at what happens in production. Real-world telemetry from organizations using AI at scale. Apiiro, 2025. Analyzing tens of thousands of repos across Fortune 50 enterprises, they found that AI-assisted developers produced 3 to 4 times more commits, but security findings increased tenfold. Privilege escalation vulnerabilities jumped 322%. Each AI-assisted pull request also touched more files, meaning each merge carried a larger blast radius if something went wrong. Escape.tech, 2025. They scanned over 5,600 publicly deployed vibe-coded applications and found more than 2,000 vulnerabilities, over 400 exposed secrets, and more than 175 instances of exposed personal data, including medical records, IBANs, and phone numbers. GitGuardian, 2026. Looking at billions of public GitHub commits, they found that AI-assisted commits had a 3.2% secret leak rate versus a 1.5% baseline. That is roughly twice the rate of human-only commits. The problem is not limited to one tool or one programming language. It is a fundamental characteristic of how AI models generate code. Of all these studies, the Stanford experiment produced the most alarming result. Not because it found the highest vulnerability rate, but because it uncovered the most dangerous combination. Worse security outcomes paired with higher developer confidence. Researchers gave 47 participants 5 coding tasks where security mattered: encrypting data, creating cryptographic signatures, preventing SQL injection, and controlling file access. One group had access to an AI assistant, the other worked without one. The results on the message signing task illustrate the pattern clearly. Without AI assistance, 21% of developers produced a secure implementation. With AI assistance, only 3% did. That is a dramatic drop. But here's what makes it dangerous. The AI-assisted group rated the AI's trustworthiness at 4 out of 5. Meanwhile, the developers who actually produced secure code rated the AI at just 1.5 out of 5. The developers who trusted AI the most got the worst security outcomes. Here's how the confidence gap plays out in practice. A developer prompts an AI coding tool. The generated code is syntactically clean and compiles. Basic functional tests pass. The developer feels highly confident. Security review gets reduced or skipped entirely, and a vulnerability ships to production. The mechanism is straightforward. AI-generated code is well-formatted, compiles cleanly, and handles typical use cases correctly. There are no obvious typos, no structural mistakes, no immediate red flags. So the developer concludes the code must be fine and skips the security review that would have caught the real problem. Security flaws almost never look broken on the surface. They hide in logic, using the wrong cryptographic algorithm, missing an authentication check, allowing user input to flow directly into a database query without validation. None of these cause syntax errors or make basic tests fail. And the hidden root cause? AI is trained on insecure historical patterns, which means it produces code that works correctly but is architecturally insecure. The Stanford researchers identified three mechanisms behind this confidence gap. First, wrong library or algorithm choice. The AI suggests something that works but is insecure by modern standards. For example, an encryption function runs and its output looks like encrypted data. The developer moves on, unaware that the algorithm itself is the problem, not the code syntax. Second, edge case blindness. The AI handles the main use case correctly, but silently ignores critical edge cases. A file path that escapes outside the intended directory, an input that breaks out of a SQL query, a JSON web token with missing signature verification. A quick functional test passes, so the dangerous case goes unnoticed. Third, testing displacement. Instead of focusing on writing secure code, developers shift their attention to simply verifying that the AI's output runs. That is a fundamentally different and far less rigorous mindset. One participant in the Stanford study captured it perfectly. "I'll trust my AI for now." But the developers who produced the most secure code while using AI were the ones who actively distrusted the output, rephrased prompts to probe edge cases, and verified results independently. Skepticism was the deciding factor. AI models do not intentionally write insecure code. The problem is more subtle. They were trained on billions of lines of publicly available code, and a large portion of that code was written before modern security practices existed, or by developers who prioritized getting things working over making them secure. When an AI generates code, it predicts the most statistically likely completion based on patterns in its training data. Insecure patterns from pre-2010 tutorials and quick start guides dominate that training data. Here's how it plays out in practice. For SQL queries, string concatenation was the dominant pattern in tutorials from the 1990s and 2000s. Parameterized queries are safer, but appear far less frequently in training data. For password hashing, MD5 and SHA-1 appear far more often in historical code than bscript or Argon2, even though MD5 and SHA-1 have been considered unsafe for well over a decade. For secret management, API keys hard-coded into source files dominate early tutorials. Loading secrets from environment variables requires extra setup that beginner examples typically skip. For course headers, wildcard configurations appear in most introductory tutorials because they eliminate setup friction. Properly restricted cores requires more code and appears far less often. The AI reproduces what it has seen most often, not what is most secure, unless you make security an explicit requirement in your prompt or project configuration. Vibe coding is a development style where software is built almost entirely through AI prompts, with minimal manual review or hands-on coding. You describe what you want in natural language and accept what the AI produces, refining through prompts until it appears to work. You never read the code, and security flaws become invisible. Vibe coding makes the confidence gap worse for a specific reason. When you are not writing the code yourself, you have far less visibility into what the generated code actually does. The Escape.tech scan of over 5,600 publicly deployed Vibe-coded apps found more than 2,000 security vulnerabilities, over 400 exposed secrets, and more than 175 instances of exposed personal data. The Apiiro production data from Fortune 50 companies reinforces this at enterprise scale. AI-assisted developers produced 3 to 4 times more commits, but security findings increased tenfold. Privilege escalation vulnerabilities jumped 322%. The pattern is consistent. AI accelerates how fast code is written while multiplying security risk at the same time. More code ships per hour, more of it contains vulnerabilities, and less of it gets manually reviewed. This guide does not tell you to stop using AI assistants. It tells you that the security review step cannot be handed off to the same AI that wrote the code. Let's zoom in on the Veracode 2025 benchmark to understand the failure rates by category. Overall, 45% of AI-generated code samples failed security review across all languages and task types. Java was the worst performing language at 72% failure rate. Cross-site scripting tasks, where the AI needed to properly sanitize user input before rendering it in a browser, failed 86% of the time. This is particularly alarming because XSS is one of the most common and well-understood vulnerability types. The Armis benchmark from 2026 went even further. 18 AI coding models were tested, and every single one failed at least one security-critical scenario. That is a 100% failure rate across all models tested. Here's what makes this finding especially important. Security performance has not improved across 2 years of model upgrades. Functional code quality has improved dramatically. Models generate more correct, more idiomatic code than ever. But security has not kept pace because the underlying training data bias has not changed. So what do you do with this information? Here are 5 mitigations that work. 1. Treat every AI-generated file as untrusted input. Review it with the same rigor you would apply to code from an unknown author. Do not let polished formatting fool you into skipping your review. 2. Run a dedicated security pass after every AI-assisted session. Check for hard-coded credentials. Verify that every new endpoint has authentication. Confirm that all new dependencies are real packages that actually exist and are maintained. 3. State security requirements explicitly in every prompt. Say, this route requires authentication. Say, user input must be validated before any database use. Do not assume the AI will add security by default, because it will not. 4. Use static analysis tools like CodeQL or SemGrep on AI-generated code before committing. They catch patterns that look syntactically correct but are structurally insecure. 5. Use a separate AI agent as a security reviewer. Have it audit the code-generating agent's output with an explicit security-focused prompt. A second model with an adversarial role catches issues the first model introduced, though it is not a substitute for human judgment on critical systems. The research does not say AI coding tools are useless. It says they shift where the security risk lives. When you write code by hand, you are actively engaged with the logic. You think through edge cases as you type. You notice when something feels off. When AI writes the code, that active engagement disappears, and you need to bring it back deliberately during the review step. Skepticism is the deciding factor, not the AI tool itself, not the programming language, not the framework. Trusting AI less led to better security outcomes. Next up, Section 2.2, Common Vulnerability Patterns, where we walk through the specific security flaws to look for during your review. For more details, visit wisebuilder.dev.